Well, good morning. Rick Dorshaw with MetaBeacon. So that's one of my disclosures, and it's an honor to just participate. A double honor to be able to speak with you. My other disclosure is that I'm not a nephrologist. I'm a physicist by training, although apparently not the only physicist by training in the room, as Dr. Forney has reminded me. So MetaBeacon, what we do is, in the highest sense of the words, research and development. We do research and development on fluorescent agents. Let's see if I can make that work. So I'm going to talk to you today about our GFR device that we're making. But we also are doing development in GI function. We got, in collaboration with Bill and Melinda, we're doing some ocular angiography in combination with the NIH. Our agents were engineered to go through the renal system, so we're lighting up some of the anatomy in the renal system so abdominal surgeons can cut where they're supposed to cut and not cut where they're not supposed to cut, and then a whole portfolio of research that we can do. But I'm here to tell you about our transdermal GFR development. Now, this isn't a new idea. Back in the 1990s, Carlos Robito at Massachusetts General Hospital had a nuclear medicine variation where he injected Tec DTPA, and he had a portable Geiger counter that you put on your arm, and he could measure GFR that way by calculating the washout curve of the radioactivity. Of course, that didn't translate commercially into the hospital because of the handling and the waste of the radioactivity. And even back then, it was thought that the way to do this would be a fluorescent agent. So that's essentially where we started our research. And we thought of two ways we could do this development. One is to take known GFR agents and make them fluoresce. Another way would be to take known dyes and make them go through the renal system. Most of the dyes that are available and are biocompatible are actually excreted through the liver. So that was the two paths we took, and within each path we had several tracks. We actually were able to get this first pathway to work. It turns out that the magnetic resonance imaging agents that have gadolinium on them, we took those and we put a europium instead of a gadolinium, and that's slightly fluorescent. And then doing chemistry, we were able to make those actually fluoresce and glow. And so that was one path. But on our second path here, finding a small molecule that fluoresces turned out to be a little bit better. And we found this in the Japanese textile industry. They were using a whole bunch of essentially pyrazine-based dyes that when we looked at them, they were small, they were bright, and they were very amenable to chemistry modification. And so our whole platform of novel fluorophores is based on that. And here's some preclinical work that we did back in 2011 on one of our analogs. And so there's two mice here. The first mouse is injected with one of our fluorophore agents. The second one just PBS as a control. And I exactly forgot the timing here, but this is 1 hour. That might have been 10 minutes, 20, 30, and 1 hour. But you see, after an hour, we're all concentrated in the bladder. And these curves this curve is a region of interest over the shoulder, so you see the intensity go up from the fluorophore, and then the kidney is taking it out. And this one is the region of interest right over the bladder, so you see the fluorescent intensity go up and kind of stay there. Here's just another example of that, where I think these are rats, and another one of our agents that is renally excreted, 2 control rats, and then here you can see after an hour the agent is in the bladder. So that was the basis of it. Oh, and here's I think one of the first times we used our agent that we are now in clinical development with on dogs. So fluorescent intensity versus time, background, and then we inject, and you see the intensity go up as the agent goes from the vasculature into the tissue where we're measuring, and then all you see is the renal excretion. And here the three curves were different places of the sensor on the dog. So we went through all this clinical development. Here's the chemist in the room, if any. There's the molecule that we're going. It's a pyrazine-based molecule. The molecular weight is about 372. It's got a really large Stokes shift. So you activate it at 445. It glows at about 560. So it's about 120 nanometer Stokes shift, which is really different than usual dyes, which tend to be 20 and 30 nanometers. And we engineered the properties to have all these. Of course, it's biocompatible, but it was engineered to be so hydrophilic that it's taken out of the body by the GFR mechanism, and it has all these attributes of GFR agents. They don't protein bind. We don't have any metabolism. It doesn't photobleach. We can inject it essentially with PBS, so it's physiological formulation, and it's got really great stability. We have both the API and the formulated in PBS is stable for years. And again, it's got this large Stokes shift, which again makes it easier to develop the instrument. You don't have to use such fancy interference filters in order to separate out the emission from the excitation. So if this works, here's an animation of what we do. So we inject, goes into the vasculature, it equilibrates with the tissue. If we're monitoring at one place, you see the fluorescence go up, and then after the equilibration between the vasculature and the tissue, all you see is the decrease of the signal due to the renal excretion, and from that we can then calculate a GFR. So that's the way it's supposed to work. Here's a picture of the third generation instrument, which we hope to use later this year in our pivotal trial. But again, what happened? I did something, sorry. There's our agent. Here's the patch that'll be on the skin that has the source and the detector in it, and then it'll be hooked up to the monitor, which will calculate the GFR, and then calculate the GFR as a function of time, so you can track GFR. And let's see, in the interest of symmetry, because I'm a physicist, this is our preclinical device, which we actually sell right now, that you can put on rodents and animals, and maybe some of the researchers in the audience already have that. I do this out of deference to my partner Daniel, who heads the division that makes our preclinical device. So, our clinical program for the GFR. What we started out in our first pilot study is using subjects that had normal renal function, and then we're in the midst of doing our pilot 2 and 3, which are subjects that have normal renal function down to stage 4 CKD, and then at the end of this year we'll do this multi-center, multinational pivotal study. So the pilot 1 design, again, for the normal renal function subjects, here's what we're doing. We're injecting our agent, which designated as MB102. That's our fluorescent agent with the 120 nanometers Stokes shift. We inject that, and then we inject iohexol in the form of Omnipaque 300. And we do three things. We collect all the urine from the subjects post-administration, with the idea to see how much of the injected dose goes into the urine, because if you want a renal agent, you kind of want most of it or all of it to be in the urine. We take plasma PK of both of our agents there so that we can compare the pharmacokinetics and show that hopefully the clearance of our agent, or the GFR of our agent, matches the GFR of iohexol, which both the FDA in the U.S. and the EMEA and the European Union have said we could use as the standard of truth. And then the last thing is we put our prototype transdermal fluorescence detector on the subjects and show that and measure the fluorescence pharmacokinetics and compare that to the plasma pharmacokinetics of our agent. So Again, some of the data here. Again, this is from our first pilot study where we're doing normal kidney function subjects. So the subjects are monitored for blood draws and urine collection for 12 hours post-administration. And what we're finding is that essentially we get all of the fluorescent agent in the urine after 12 hours. And again, the agent is about a 2-hour half-life, so 6 half-lives later we're getting it all, but it's all renal, and it compares really favorable to the iohexol, which is the standard. Here's a PK profile from one of the subjects. So the red dots are the 15 blood draws we do over the 12-hour period. The blue line through there is not really predicted. That's a fit to a 2-compartment pharmacokinetic model using the standard software. And what you see is, on the log plot, you see the 2 compartments. This is the vascular to tissue equilibrium, and then the long line here is the renal excretion. And the one slope here indicates, a particular GFR. One way to calculate that would be the dose over the area under the curve. Of course, we used the software to do that. Because we're using HPLC in order to measure the agents in the plasma, one can tell something about the metabolites. So the pink line, which you can barely see here, is before any injection. The black line is 30 minutes, our 30-minute time point. All you see is the agent. You don't see any metabolites. So at least on the scale that we're able to measure, we have negligible metabolites in the plasma. The same thing is in the urine. The agent goes in, does not interact with the body, and comes out intact. Okay, so from the plasma pharmacokinetics, you can then calculate the clearance, or the GFR. So we do that. So the GFR of our agent, we plot it against what we get for the GFR of iohexol. In our first half of the pilot study, 16 of the subjects got this really low dose, about 100 times less than iohexol. You can see the 16 dots there. The solid green line is a regression through there with really a fantastic R squared. There's 2 things here maybe to note. Again, these subjects were enrolled to have normal renal function based on their serum creatinine. And of course, on the measured values here, you see several of them have, less than maybe 80 mils per minute. So even though the serum creatinine says that they're normal, they're really not. So again, this is why you probably need to use a direct measure of GFR as opposed to the eGFR equations. The other thing you might note, if you really squint, you see that the regression line here is a little bit different than the identity line, and again, that had to do with the dose. GFR is dose over area under the curve. We were injecting our agent with really small syringes. The iohexol is a standard 5 mil syringe, or 5 mil injection in a 10 mil syringe. There was some difference in the syringes that we think accounted for that, because when we did a higher dose, which is here, we did 8 subjects at this higher dose, which I needed to use in order to actually see the transdermal fluorescence, which I'll show you in a moment. But now the doses and the syringes were the same, and you get almost perfect, perfect overlap with the GFR of our agent with iohexol. Plus, on just 8 subjects here, we get a really great R squared. So we're really happy with that. So showing that the GFR is the same, and showing that the percent injected dose in the urine is 100%, essentially showed that this is in fact a GFR agent in man. So we went next to our transdermal measurements. So our first generation transdermal measurement was actually a box with the source and the detector in it, and we had fiber optics coming to the patient, made it a little bit unwieldy, so we went out to about 4 hours in terms of that measurement. But here you see the fluorescent versus versus time, a little background, then we inject. You see the fluorescence go up. That's the blue dots. And then the kidney starts taking it out. The red line here is, again, a fit to a 2-compartment model. So again, we get 2-hour half-life in the normal renal function subjects. If we do a 1-compartment and start here, you get the same numbers. If you plot these as the log, you can kind of see the long GFR renal excretion there, and there. We did this on subject. We divided up the dermatologists. Your dermatology colleagues have divided the world into 6 skin colors, and so we, by visual aids, just did that. So we had different colored skins. So this is supposed to be Caucasian. You can see we can do the measurement. This person was either Hispanic or Asian, and again, we could see it by adjusting the powers and the amplifiers. And here's a black person who, again, we can measure. Because our first generation prototypes were kind of bulky, the attachments started falling off around 4 hours, so that's what that is. In order to show that the plasma, the transdermal pharmacokinetics match the plasma, we did it this way. Here's our subject, subject number 12. This is his plasma pharmacokinetics. At the same time, he's got our transdermal measurement on it, and that's the transdermal measurement. So you see the intensity go up and come down. These big red dots are overlays of where blood draws were taken. So we could take the 4 spots here on the renal excretion on our fluorescence, so we can match the fluorescence with the 4 blood draws over here. And if we do that, we get like a perfect correlation, meaning this slope here is the same as that slope in terms of its correlation, and the transdermal pharmacokinetics match the plasma pharmacokinetics. So that was the third and final kind of endpoint we wanted to do. All 8 subjects that had the higher dose where we can measure the fluorescence had these perfect correlations. So the end result of our Pilot 1 study was exactly that we covered all the dose. The plasma measured GFRs match our agent with iohexol. Our agent's plasma pharmacokinetics match the transdermal. For normal renal function, we could probably measure 6 to 8 hours. And you can imagine if you had impaired renal function, you would measure longer. And then we have our agent on stability. It seems to be stable for years. So in conclusion, I'll give you a little teaser. Our Pilot 2, where we did from normal renal function down to stage 4, we did that at... We did the same thing. We're going to measure urine. We measured the plasma pharmacokinetics of our 2 agents, and we used our second generation device. This was done in St. Louis at these 2 universities, and those results are being compiled. We just finished that. The results actually look really good, and they'll be presented at ASN in 2017. So I want to thank you very much.